We continue our course, second part. So today we start with the superconductivity, and all this week we'll proceed discussing superconductivity. 4 lectures, and next week concluding 4 lectures will be about magnetism. So today is lecture number 9. We will have several small chapters today. So the general title would probably be Superconductivity Part 1. Let me start with listing a few experimental facts. And the puzzle. So in 1911, the Dutch physicist Caroline Onnes observed that if one takes a mercury and measures resistivity of mercury at low temperatures, that at some temperature, which is about 4 Kelvin, the temperature drops completely and the resistivity becomes 0. So this is how resistivity looks like. This is TC. And therefore, since that time, metals which conduct current without any resistance are called superconductors. So it was clear from the very beginning that not all metals are superconductors. For example, copper, being cooled down up to very low temperatures, does not superconduct. And besides, temperatures of superconducting transition for different metallic materials vary in quite a big range. So, as I said, let me put TC here. It's about 4 Kelvin for niobium. It's higher. It's 9.25 Kelvin. For tungsten, it's much low. It's 0.015 Kelvin. And since 1911, there was a race to find a material with highest possible TC. All these temperatures are in the range of liquid helium, helium form, and as we discussed it last month, helium is superfluid, and it's quite expensive to first of all produce it. Only few countries in the world do commercial production and sell helium, because this is byproduct of gas and oil industry. This is how people get it from the earth, and from practical means, it's quite expensive to use superconducting materials. Therefore, for more than a century, the goal is to find, design, engineer, or whatever material with TC, with a critical temperature, which would be at least in the range of liquid nitrogen. So, in liquid nitrogen, temperature is 77 Kelvin. So, if one can use nitrogen for cooling down metals, which then be superconducting, it will be a great achievement. And what happened that until 1985, so for almost 75 years, the best possible material was niobium-3 germanium, with a TC of about 24 Kelvin. So you see that this is not that much. However, in 1985, there was a revolution in the sense that the new material with which is lanthanum to copper oxide was discovered with critical temperature not that big. So it was only 40 Kelvin, which is still below the temperature of liquid nitrogen. However, the revolution was that before people were looking for metals and alloys which are metallic, and the new material was a ceramic. And almost the very same year, it was another material, yttrium, barium 2, copper 07, this is copper 3, yeah, with a temperature over 90 Kelvin. So, bingo, the goal was achieved, and for last 30 years, actually, people were increasing the number of materials which are belonging to the same family. These are copper oxide, all of them are ceramics, and at the same time looking for other materials. So good thing about these systems is that it's indeed characterized by high enough temperature of superconducting transition. However, there is a bad thing. As I said, these materials are ceramics, therefore basically it's a powder, and technologically it's very difficult to make wires out of these materials, because in order to make a wires, to produce superconducting magnets, for example, one needs certain plasticity and avoid any cracks or whatever. These materials are unfortunately not technological. So for more than 10 years, people are studying and investigating yet another family of new materials, which are so-called iron-based superconductors, which are based on iron and arsenicum, or iron and selenium. We discussed this new development of materials and elements and physics of strongly correlated systems, because certainly these new materials do not fall into the universality class of theory, which I'm going to discuss during next 4 lectures. We discuss all this new stuff on the very last lecture of the course. So, as I said, the first fact behind the certain behavior of new materials, and this is indeed new phenomena, is drop of the resistivity. However, there are a few other intriguing facts. For example, let me say that this is number 1, and number 2, if we take usual ordinary metal, let's call it normal metal, and put it in magnetic field, then magnetic field penetrates into the metal and nothing happens. However, if we take a superconductor, then what we see, and for the moment I'm going to speak about so-called type 1 superconductor, that the magnetic field does not penetrate into it. So this is superconductor. This is another interesting phenomenon, which is called Meissner Effect. And actually, both effects, namely drop of resistivity and Meissner effect, is used to detect superconductivity and moreover determine the critical temperature. If you speak with about new material, if you heard the talk, the first question which people ask, is Meissner effect observed or not? Or do you see the drop of resistivity or not? If none of this effect is pronounced, people typically are very skeptical and start to discuss that that might be proximity effect or whatever. So these are two key observations. So today we actually construct very simple theory which explains the Meissner effect, and this theory will be based on our previous knowledges about superfluidity. We start with a phenomenology, namely two-component model, and after some almost trivial calculations, we will see that the existence of superfluid liquid is sufficient to explain the Meissner effect. The penetration depth, so the skin where the field can penetrate into the superconductor, which is called London penetration depth, actually depends on the temperature, and this is again experimental observation as 1 minus T over Tc to the 4th power n squared. I'm listing you the experimental facts. Then, number 3, measuring specific heat of the superconducting materials in the superconducting phase or close to the transition point actually result in observation that specific heat has a jump at Tc. So this is specific heat and this is temperature. And besides, this behavior at low temperatures is exponential, minus some delta over temperature, which immediately led to conclusion that the spectrum of elementary excitations below Tc is gapped. You probably discussed with Professor Nersisyan thermodynamics, and you should know that as soon as you get a gap, the specific heat will be exponential, while if you don't have gap, for example, you take 3 fermions, the spectrum is linear, excitations are gapless, you have a linear contribution to specific heat, you take phonons, another gapless excitations or magnons, and in 3 dimension you have T cube contribution to specific heat. So here it's a gap, and gap continuously changes when the temperature is increased, and therefore the conclusion was that transition into the superconducting state was second order phase transition. Besides, it was interesting observation, which is so-called isotope effect, which says that critical temperature, when you change the isotopes, and sometimes it's possible, there are several isotopes of the same material, that the critical temperature is inversely proportional to the square root of the mass of the isotope. So this is so-called isotope effect. Which actually allowed to conclude that it seems that the phenomena of superconductivity has something to do with phonons. You have your solid state physics course, you consider one atomic diatomic lattices, and you calculated eigenfrequencies in a lattice, a system of coupled oscillators, and as in classical mechanics, you know that eigenfrequencies are inversely proportional to the square root of mass. Okay, then yet another measurement which was done actually was electric measurement in putting normal and superconducting materials in a contact and attaching it to the battery and measuring the IV curve, so measuring the current function of applied voltage to the junction. We know that for standard metals we have Ohm law, which says that the current is proportional to applied voltage. However, in this NS junction, so to say, the linear dependence of current as a function of voltage was achieved asymptotically only for sufficiently high voltages. Besides, the current was zero up to some critical voltage, and then it saturates to linear behavior. Which means that, again, there is a gap in the spectrum of excitation, since, as we will see soon, the current is proportional to the density of states, and gap in the spectrum means that your density of states is gapped at the Fermi level. Okay, what we can conclude from these few observations, that certain materials do behave as superconductors, namely they conduct electric current without energy losses, and there is a gap in the spectrum of elementary excitations of these materials. We don't yet know what is the mechanism. I mean, I didn't tell you what is the mechanism of superconductivity, what is the object which superconducts. However, there is a phase transition, and second order phase transition means that there is a spontaneous symmetry breaking in the system, and as a result there is something charged which produces current without energy losses, and this is a phenomenon of superconductivity. But before we come to microscopic theory of superconductivity, which I'm going to discuss on Wednesday, today we discuss phenomenology of superconductors, some attempts to explain this phenomena utilizing the analogies between superconductors and superfluids, because it was clear to the people that these two phenomena are closely related, because superfluidity is ability of certain materials like liquid helium flow through the capillaries without friction, and superconductors is related to charged superfluid, which actually supports the current without any energy losses. So therefore it was quite natural. Let me assume now the picture. The little paragraph which we are going to discuss now is electrodynamics of superconductors. That two-fluid phenomenology could work. So therefore, similar to the system with the BEC and superfluidity, namely interacting system, we will assume that we can characterize the superconductor by the wave function, which is going to be the order parameter, as we will see on Wednesday, and this wave function, which is the same as the wave function of condensate, depends on R as square root over Ns. This is superconducting density of superconducting compound times I chi phase, which depends on R. Therefore, this is pretty the same as we did for superfluid. Now we can write down quantum mechanical expression for the superconducting current. Now this is charged current. For superfluid, we discussed the mass current. Therefore, it is I h bar over 2 m star. I will put m star because I don't know what is the mass of the carriers. Then, since it's a charge current, I should multiply it by the E star, because I also don't know what is the charge of superconducting current. On Wednesday we will see that, or even today we will see that in fact what happens is that two electrons form a Cooper pair, so-called Cooper pair, so they're paired, and these Cooper pairs are producing superfluid or superconducting current. Therefore, at the end of the day, let me put it here, we will see that E star is equal twice the charge of electron, and effective mass is twice mass of the electron. By the time the Ginzburg-Landau theory was constructed, scientists introduced effective charge and effective mass, and actually interestingly commented that interestingly to fit the experiment, these notations, these notions should be taken into account, but interestingly also they didn't draw any conclusion about the nature of superconductivity. And while the Ginzburg-Landau theory, which we are going to discuss on Wednesday, was constructed in 1950, you see it took almost 40 years to come to simple phenomenological theory. The microscopic theory, which we are going to discuss on Friday, was constructed in 1957. So the current, charge current, is psi gradient psi star minus psi star gradient psi. So we assume that the condensate is uniform, the density doesn't depend on, very slowly depend on the radius vector. We plug in this wave function here, compute the derivative, which is I h bar over 2 m star E star. So since it's a product of two wave function, I will write ns, and here I have e to the power I chi. Now it's gradient of minus I chi times e to the power minus I chi minus e to the power minus I chi, gradient of I chi e to the power I chi. So you see that exponents actually cancel out. Here I have minus I, and here I have yet another minus I, and therefore the superconducting current minus I times I give me 1. I have h bar E star divided by m star nc times gradient chi. So this is the same expression for the current, except I multiplied everything by the charge. This is not a mass current, which we obtained from the superfluid. However, here we need to make a comment. I would like to add a magnetic field to the system, and in order to do it, I need to recall that the current is measurable quantity. It should not depend on the gauge, so therefore it should be gauge invariant. So I would like to send you back to your lectures on quantum mechanics and recall how do we show that the quantum mechanics is gauge invariant. So let me add plus magnetic field. And recapitulate that the gauge invariance assumes that if we have a vector potential A and magnetic field B is just the vector product of nabla and A. This is how we have magnetic field. So we can add to the vector potential any gradient of a function, any function of R. Because the operator nabla, which is applied to the gradient, produces 0. And therefore, at the same time, we have to replace the wave function to the wave function, which is a product by I E star over H phi, and there is also C. Let me keep both. Speed of light and H bar. If we do that, we clearly see that this equation in magnetic field is not complete. Namely, our function chi then will be replaced by chi plus I E star over HC phi. Which means that there will be something added to, sorry, without I. Added to the current, which actually vary physical. We do a gauge transformation and we see that the current depends on gauge. In order to avoid it, we actually should replace gradient chi by gradient chi minus E star over HCA. And you see that if this change is done, then under this transformation we get this phase which is added to chi, and we have also this phase added because of phi, and then they cancel out. So therefore, the current consists of paramagnetic part, and this is nothing but diamagnetic part, the supercurrent, superconducting current, in the presence of magnetic field, should be written down as H E star over M star and S. Here we have gradient chi minus E star over HC. So this is a gauge invariant expression for the current, which doesn't change under the gauge transformation. Okay? So let's now derive something which would be called as London equation. London and London are two brothers. It has nothing to do with the capital of United Kingdom. So let's apply operator nabla to GS and see what happens. So we have two terms. Well, I'm applying nabla to the gradient, we get 0. So what we have at the end of the day, we have only nabla applied to the vector potential A, and then we have sign minus H star H E star square divided by H bar M star C and S, and H bar is cancelled out, and here we have a nabla applied to the vector potential A. So this is precisely the magnetic field. So I will continue it here. This is minus E square over M star C and S B. On the other hand, we have Maxwell equations, right? which says that operator nabla applied to beam is 4 pi over c gs. This is one of the Maxwell equations I'm going to use. And second Maxwell equation says that the divergence of beam, so the scalar product of operator nabla and beam, is equal to what? 0, right? Because there are no magnetic charges. Good. So these two Maxwell equations being combined with the equation for the supercurrent, and the equation for supercurrent reflects the fact that we have a wave function to describe the condensate, describe the superfluid state. So what I will do next, I will apply operator nabla to the left-hand side and right-hand side of this equation, namely nabla times beam is equal to 4p over c times nabla gc. Therefore, this is minus 4p over c times e star square over m star c and s b. So I got equation, and what I need to do is to simplify the left-hand side. Okay? Let's do that. In order to do that, we need to produce very simple calculation. So nabla times beam, as we see that this is vector, I will take the alpha component of this vector. Okay? You should be familiar with the way to write down these expressions. The best way to do it is to use so-called Levi-Civita tensors. So by the definition, this is epsilon, alpha, beta, gamma. So this alpha d or dx beta over gamma component of this. So this is epsilon, gamma, mu, nu, d or dx mu, b, u. Okay? Do you understand what I have written? Are you familiar with doing these calculations in tensor form? You follow me? So we have two fully antisymmetric Levi-Civita tensors. The index alpha, beta, gamma runs from 1 to 3, or x, y, z. This is a Cartesian component. And this is so-called Einstein notation, which assumes that any repeating indices means summation over these indexes. We have repeating indexes here, we have repeating indexes here, we have repeating indexes here, we have repeating indexes there. So as a result, the only free index is alpha. Besides, the Levi-Civita tensors epsilon, as I said, are fully antisymmetric tensors, which are equal to 1 if we have the ordering of alpha, beta, gamma this way and any cyclic permutation, or it is equal to -1 if we flip any pair of these indexes, or we have anticyclic permutation. Besides, so therefore I can put index gamma and cyclically permute it here. We have epsilon gamma beta alpha, sorry, gamma alpha beta times epsilon gamma mu nu. So index gamma doesn't enter anywhere, so we can take summation over gamma of these two tensors. Again, it is known, you can check it and prove, that summation over repeating index gamma of product of two Levi-Civita tensors is equal to determinant written in terms of Kronecker symbols: alpha mu, delta alpha nu, delta beta mu, delta beta nu. which is delta alpha mu delta beta nu minus delta alpha nu delta beta nu. So I'm going to plug it into the first line. So we have this nabla times B alpha component is equal to, first term, alpha is equal to mu, beta is equal to nu. So we have d over dx beta, mu is equal to alpha, d over dx alpha, nu is equal to beta, beta. This is the first term. We still have a summation over beta. Okay? This is the first term. Plug it in there. Minus. Now alpha is d over dx beta. D over dx mu is equal to beta. And mu is equal to alpha. B alpha. So let me interchange the two differentiation here. I will write it as d over dx alpha db beta over dx beta. Right? Minus d2 over dx beta square b alpha. What is that? I use the second Maxwell equation, which is db beta over dx beta. So therefore the first term is equal to 0. Therefore this is minus Laplacian, and I can write down the equation as minus Laplacian b is equal to minus 4 pi e star square over m star c square nsb. So I obtained very nice and simple equation. Okay? Please practice yourself in computing. This is very simple and very efficient. This should be part of your curriculum. You should be able to do these calculations day and night. Now let's introduce shorthand notations. I would like to introduce the coefficient 1 over lambda square as this coefficient 4 pi e star square divided by m star c square ns. Therefore, my equation reads nabla b minus b over lambda square is equal to 0. Okay? Now, let's be back to what I sketched here. Suppose we have the flat boundary between superconductor and normal metal and magnetic field. So this is Z, and magnetic field, which has 3 components depends only on Z. So we will assume that in this geometry B is function of only one coordinate, because the magnetic field is directed this way. So let's first look at the Z component of this equation. So this is vector equation, therefore we can write it down component by component. So we're looking for Z component. So therefore d over dz, dbz over dz is equal to bz over lambda square, right? But since b depends only on z, the divergence of B is equal to 0 means that dBz over dz is equal to 0. This comes from this equation because the field doesn't depend on x and y. Okay? So therefore, this equation simply means 0 is equal to Bz over lambda square, which can be read as Bz is equal to 0. So, in fact, this equation immediately tells us that the normal component doesn't penetrate into the superconductor. What about the parallel component? So now, we say we are looking for B parallel, which depends on Z. Therefore, it's d2 over dz square minus B parallel Z divided by lambda square is equal to 0. This equation has a very simple solution, which says that B parallel as a function of Z is equal to B parallel at the boundary times exponent minus Z over lambda.
So now B equals to depends only on Z. Is it from the symmetry, cylindrical symmetry?
No, we're saying that magnetic field goes this direction. It comes from the geometry of the problem which I'm going to solve. Of course, if I will use a ball into the superconductor or cylinder, I need to apply different conditions. I'm using very simple calculation. So we have flat boundary and we have superconductor to the left and normal metal to the right. And we apply magnetic field this way. Okay, so therefore, this is the definition of penetration length, and actually what we did, we explained the Meissner effect. Coming back to our initial assumptions, what we did and why we explained the Meissner effect, just because the key point was that we assumed that there is a condensate, that there is a superfluid state which can be characterized by unique global wave function, and using gauge invariance we wrote the expression for the supercurrent, and all the rest is just technical calculation. By the way, we can repeat the same calculations for the J, and we will get the very same equation, which means that there are no currents inside the superconductor. All currents are in the skin of the width lambda, and these currents screen magnetic field. This is why the magnetic field is not penetrating. So my suggestion is rewrite these equations in terms of the current. So write corresponding equation for the current. One can do it using vector potential. Actually here, this is equation. One needs to plug it in this and use a connection and prove that the same solution can be obtained for the supercurrent. Okay? Do it. Good. By the way, this equation for the supercurrent is known as the London equation, and typically people refer to two London equations. There is yet another way to derive it using second pair of Maxwell equations. I don't have time for doing that, but two London equations, if you need in the literature, in these notations is this equation and equation that divergence of A, we use a special gauge, namely we use gauge divergence of A is equal to 0, because we will need it when we apply the gradient. Good. Any questions about that? This is still phenomenology, and I will keep doing phenomenology of superconductors. This is the status of theory on 1930-1935. You see, the understanding of superconductivity was very slow. And now, let me go to yet another chapter, small chapter, which is electron-phonon interaction. I already noticed that it looks like, because of isotope effect, that the superconductivity has something to do with phonons. Therefore, what we would try to build now is a mechanism which provides an attraction between electrons through the lightest vibration. So, electron-phonon interaction. Did you discuss it in the course of solid-state physics? So you know how to write down the effective Hamiltonian of interaction. I would not be able to spend the lecture for that. I would just like to sketch the logics. And the logics is as follows. We write down the correction to the energy associated with interaction between electrons and the lattice vibration. So delta energy associated with phonons, electrons, let me see, is then given by the integral. We have minus E. We have electron density. Because we use Bohr-Oppenheimer, we have adiabaticity. Electron density at the point R. We have some kernel which is interaction R minus R prime. And we should write down connection with the divergence of polarization in the point R prime. So this is integral over dr prime. So this is electron-electron interaction. We have metal. In metals, as we discussed it by computing the electron constant, we have a screening. So K R minus R prime is nothing but 1 over R minus R prime, the Coulomb interaction, if R minus R prime smaller than d by radius, and it's you cover potential 1 over R minus R prime e to the minus R minus R prime or d if R minus R prime is larger than Rd. We computed the electric function, we identify the screening regime, and we said that in metals the electron-electron interaction is very efficiently screened, such a way that this d by radius, we are in the limit, the Fermi momentum times Bohr radius of the order of 1, in principle should be much larger than 1. We discussed that this is almost ideal Fermi system, but in real metal, d by radius is of the order of lattice constant. So this is of the order of inverse Fermi momentum. The units of h bar is equal to 1. Therefore, our potential is almost delta functional. So it has very small tails because it's exponentially screened. So first thing what we do, we replace this by delta function R minus R prime. This is first thing what we do. Second thing, this we write down that this is divergence of polarization, and polarization is proportional to the displacement. So what happens that ion moves, you have a displacement, you polarize media, which then interacts with electron density. So there is some proportionality constant C times D, where D is the displacement. So by plugging, and this is, by the way, real field of the phonons. So having done that, we can write down that the Hamiltonian of E phonon interaction is now local, some constant G, integral over dr. This is psi star r psi r times real field of the displacement. Okay? So then we can quantize our displacement. This would, since this field is real, this would be B plus B dagger. We can quantize our electron field. So this is the density. Psi are electron fields. And as a result, we can write down this Hamiltonian as sum over Q, some amplitudes AQ, A dagger K minus Q A K, sigma sigma, electrons have spins, and here we have BQ plus B minus Q dagger. So we have this Hamiltonian of electron phonon interaction, where these amplitudes, complex amplitudes, will be inversely proportional to the square root of the mass of the ion. I hope you have something like that in the derivation of electron phonon interaction in the course of solid state physics. Okay? Did you get this Hamiltonian or anything like that? Did you discuss something like that with Professor Mersison? Good. He probably introduced his way to derive it. But this is the essence. Let me again present it pictorially. What happened? We have electron with a wave vector k and sigma, which this is k minus q. Therefore, we can associate the first term in the Hamiltonian with emission, with absorption of the phonon with the vector q. So the electron, I probably need to write plus q. Let me see. No. If I do it this way, of course, I should write q. Let me write it this way. I will write V dagger q and here B minus q. Because I annihilate, and this will be minus q. This then will be correct. So, what happens is I have a conservation of energy and conservation of the momentum. I have sum of the momentum k minus q and q, which gives me k, and this is k. This is a process of emission of the phonon. And then I have yet another process. I have k minus q, and then I can absorb the phonon with a wave vector minus q. So this is emission, and this is absorption. Okay? This is what we have here. Again, we create the electron with k minus q. We create a phonon with a vector q, and we annihilate the electron with k. And since the interaction with the lattice vibration doesn't change the spin of electron, we can keep spin as a silent index. Good. But what we want to do now, we want to take a phonon as a mediator. So we would like to see how the electrons can interact between themselves through the phonons. Therefore, what we need to do, we need to actually take a second order of perturbation theory and take a phonon as a mediator. For example, what I would like to do is to consider the following processes. So this is K, this is K minus Q, this is Q. This is K1, and according to conservation of the momentum and energy, I have to write down K1 plus Q. So this is the process originating from this diagram when I take the complementary one. And I can take into account another process associated with this diagram, K minus Q, K minus Q, and I have K1 and K1 plus Q. Okay? So this is emission, emission absorption, this is absorption emission. So as a result, I will get a Hamiltonian where two electrons interact through the exchange of the phonons. Okay? So using perturbation theory, I will calculate now the matrix element of this process. So this is second order perturbation theory. Therefore, this correction to the energy is equal to sum over all intermediate state. I need to take VES, VS finite, E all intermediate state S, E minus ES. So E means initial state, F means final state, S means all intermediate states which I take.
Sorry, Professor, in the second diagram, the emission is K1 minus Q?
Yeah, I have a conservation law. Look, K plus minus Q should be equal to this. So K minus Q, K minus Q. And here, K1 and K1 plus Q minus Q is equal to K1. And actually, here we have these matrix elements which are AQ. So let me say that this is diagram A and this is diagram B. Again, this is indeed Feynman diagrams, but you need to look at this just as a presentation of processes which we use. This is very good language. So for diagram A, what we have, we need to sum up. We take two electrons. Actually now the picture which we would like to keep in mind. Let's take spherical Fermi surface, and since we are talking about excitations, we will take states very close to the Fermi surface. So I will say that initial state is this K, and the final state is state with a K minus Q. Therefore, we need to take a summation. So here initial state corresponds to epsilon k minus the final state is epsilon k minus q plus h omega q. So we emit phonon with energy h omega q. And in the numerator we have a q modulus square, because this is a vertex a q, this is a vertex a minus q, but since the Phonon field is real, we can write down that a minus q is equal to a q. A minus q is equal to a q star, the same way as you did it several times with the Professor Narcissyan. Therefore, for the diagram A, we have this, and we need to take a summation of all intermediate states, namely summation over all q. Now, if we consider correction to the energy. So, the diagram B we have sum over states. Again, we have epsilon k1. I just look at this diagram from the right hand side. Minus epsilon k1 plus q plus h omega q. I use the fact that the frequency of the Phonon mode is even function of q. Therefore, q or minus q doesn't matter. And I have a q modulus square. However, let me write down the conservation of energy, which means that epsilon k plus epsilon k minus q is equal to epsilon k1 plus epsilon k1 plus q. This is a global conservation of the energy. Therefore, epsilon k1 minus, I'm writing nonsense. I should write that epsilon k plus epsilon k1, these are two processes, incoming processes, are equal to epsilon k minus q plus epsilon k1 plus q. So this is two ongoing processes, this is two outcoming processes. So therefore epsilon k1 minus epsilon k1 plus q is equal to epsilon k minus q minus epsilon k. Therefore, this diagram, epsilon k1 minus epsilon k1 plus q, is equal to minus sum aq. Here I have epsilon k minus epsilon k minus q plus h omega q. So here I have minus, and here I have plus, because I will replace this and I will take overall minus. So let me now forget about correction to the energy and speak in terms of Hamiltonian. I have this sum over q, I will drop it off, and I will just take the sum of these two processes. So this V effective which I can interpret as effective interaction, this is a q modulus square and I have sum 1 over epsilon k minus epsilon k minus q minus h omega q minus 1 over epsilon k minus q plus h omega q. This is indeed two absorption and emission processes. In the pole, I emit or absorb. So this is then aq modulus square times 2 times h omega q divided by epsilon k minus q square minus h omega q square. This is effective interaction, which depends on k and q, which is sum of these two processes. Now let's go back to this Fermi. Suppose that the difference of energies of two electrons, namely this term, is much smaller compared to the characteristic frequency. Of course, we are going to take the optical phonon, right? Therefore, the characteristic frequency here is the bifrequency, and we can drop dependence on the q. So we are talking about interaction of two electrons in the vicinity of Fermi surface. Let me finish my statement and then I come back. Under condition epsilon k minus q smaller than h omega the bi. Question.
Why we take the optical phonons?
Because if we have something beyond the monoatomic lattice, we have optical and acoustic phonon. I don't want to consider so-called soft mode. I assume that there is always optical mode characterized by the bifrequency to make my theory simple. And frequency, namely the bifrequency, will be characteristic frequency which will determine the critical temperature of superconducting transition, as we will see quite soon. So let me apply this condition. And this is why I need the bifrequency. If it is so, I can drop this term and get minus aq modulus square divided by, so this is twice, h omega q. So what I obtain, that effective interaction between electrons, and this is what I consider it, subject to phonon, electron-phonon interaction. So effective electron interaction mediated by phonons is attractive. So this is negative, provided that two quasi-particles are taken very close to the Fermi surface. You remember that in Fermi liquid, quasi-particles are well defined when they are very close to the Fermi surface. Besides, I define the skin of the Fermi surface of the thickness of a twice dBi frequency, where the electrons can pair because they are subject to attractive interaction. Did you get how I obtain attractive interaction? So I took the perturbation theory, I identified two processes, I sum them up. So if it is not the case, if the energies is higher than this skin, of course this term will dominate and the interaction is of course repulsive. So I truncate my skin near the Fermi surface, and I will consider only those electrons which are in this thin skin. And these electrons, according to these calculations, will attract each other. All the rest calculations, all the rest electrons will repel. This will attract. I will show you on some small short movie that in fact what happens, that the vibrations of ions create a kind of trapping potential. So the ions are vibrating on the lattice, and they are creating a trapping potential such a way that two electrons can form a pair. So now we see that electrons, if I take one electron here and one electron there, this is what I'm going to do next. will attract each other and form a bound state, which is a Cooper pair. Actually, I will use this Hamiltonian with attractive interaction on Friday and construct the microscopic theory of superconductivity. We will do UV transformation, diagonalize this Hamiltonian, assuming that there is macroscopic number of Cooper pairs, and obtain that the spectrum of elementary excitations is gapped. But what I would like to do now, I would like to solve so-called Cooper problem. So I would like to show that two electrons taken in the vicinity of the Fermi surface form a bound state. Okay. So-called Cooper problem, which was the cornerstone of the Bardian-Cooper-Schrieffer theory. Cooper is the name, Leon Cooper pairing. So, this is the picture which we are going to have in mind. We have two electrons, and we would like to construct a solution of Schrödinger equation for the wave function of two electrons. So we have R1 and R2. The electrons are identical indistinguishable particles, and therefore we come to and you know, we are in the Fermi liquid, so this wave function will be constructed out of the plane waves. So we have I k1 R1 plus I k2 R2 with some coefficients. This is what we are going to reshuffle. So I'm constructing the wave function. So first of all, I would like to introduce the variables of centrum of mass and the relative motion. So I will say that R is R1 plus R2 half, and rho is R1 minus R2. At the same time, I can introduce the centrum of mass momentum K1, which is K1 plus K2, and momentum Q, which is K1 minus K2 half. So this is a momentum, this is a coordinate of centrum of mass, this is momentum of centrum of mass, this is a coordinate of relative motion, and this is a momentum of the relative motion. So my wave function, which depends on R and rho, can be expanded in terms of the basis of plane waves. So this is sum e to the power I k r plus I q rho, and there will be some coefficients C, Q, which depend on the K. Okay? So this is, so the sum is over Q and K. So what I would like to write, what I would like to do next, I would like to write down a Schrödinger equation and solve it assuming, making certain assumptions about potential of interaction between two electrons. So in addition, I will introduce the total mass. You know, the two-body problem in classical and quantum mechanics can be related to the single-body problem. And if we are in the centrum of mass, this is a single-body problem of a particle with a reduced of mass. So m is a total mass, something which is associated with the kinetic energy of the centrum of mass. So this is m1 plus m2, but since masses are equivalent, are identical, this is 2m. And I will also introduce reduced mass. 1 over mu is 1 over m1 plus 1 over m2. So therefore mu is m over 2. This is a total mass, this is a reduced mass. And I start writing. Any problem with? I start writing the Schrödinger equation written on the coefficients kq. So I have kinetic energy k squared over 2m total, therefore this is 4m, plus q squared over 2m reduced, therefore this is m, plus sum over q1 v q q1 c q1 k k square over 4m plus q square over m times c q. K plus is equal to E times c q. Yeah. So this is a Schrödinger equation which is H psi is equal to E psi. Okay. We derived that sort of Schrödinger equations when we computed the dielectric function of metals. So just to remind that the V Q Q1 is just a matrix element over e to the power minus I Q1 rho V rho. The effective potential, of course, depends only on the relative coordinate rho e to the power I Q rho and d rho. So this is a Schrödinger equation. Now I will assume that my potential V Q1 is a constant minus modulus V if epsilon Q minus epsilon Q1 is smaller than H omega d and 0 otherwise is larger than H omega d. You have a problem in your homework which actually is asking how to solve the Schrödinger equation in cylindrical well and find the bound state. So, therefore, what I have here, I will transfer this term into the left-hand side and this term into the right-hand side. So what I have is k squared over 4m plus q squared over m minus energy cq is equal to modulus v sum over q1 c q1, and the sum assumes certain summation. I will put it as a sum prime, where sum means that this rule is applied. Let me divide the left-hand side and right-hand side over this multiplier and take a summation over q. So what I have in the left-hand side, sum over q CQ is equal to sum over q 1 over k squared over 4m plus q squared over m minus e modulus v divided multiplied by CQ1 CQ1. Again, I will take the very same summation over q, assuming that I'm summing up only over state in the vicinity of Fermi surface. So this condition tells me that I select a scale over thickness of 2d frequency, and I'm only taking into account the electrons. So, therefore, I will cancel out this and that, right? And as a result, I get equation as 1 is equal to modulus v, sum prime over q, 1 over k square over 4m plus q square over m minus e. So this is equation for eigenvalue energy, E. If I find that E is smaller than twice the Fermi energy, because I'm assuming that 2 electrons are taken at the Fermi surface, then there is a bound state. Okay? And this is what I'm going to show. Are you with me or not? What's wrong? What's the problem? You don't understand what I'm doing? Of course, I'm telling you in 1 hour the work which person got a Nobel Prize, but still, I'm not missing any calculations, and don't sketch anything, you just follow me.
I didn't catch that part of the summation.
Sorry?
The part of the summation, why they cancel out?
Because this is the same. This is sum over q, this is sum over q1. So this is the index of summation. Sum over q CQ is equal to sum over q1 CQ1. This is the same number.
Why do you decompose that sum on 2 sums?
Well, first of all, I use the fact that the interaction is constant. Therefore, I took it out. And the object which is here is a summation over q1. This is a number. So, and therefore, I would like to divide, take a sum, this is a number, and I just cancel the number in the left-hand side and the right-hand side. This is the consequence of the fact that the interaction is constant. So I have cylindrical rectangular well, if you like. Besides, for simplicity, and on the tutorial you will probably consider more general case, I will assume that the centrum of mass momentum k is equal to 0. At this moment, I will set that k is equal to 0, which means that the momentum of the Cooper pair, so this is k1, this is k2, that the momentum of the centrum of mass is 0. So I'm sitting in the system of the centrum of mass. We will see that if Cooper pair moves like Landau criterion, there is a critical velocity, which then destroys the current. So I will assume that there is no current, there is no electric field applied to the system. So the Cooper pair doesn't move. So the centrum of mass momentum is 0. I'm sitting in the centrum of mass. So if it is so, if k is equal to 0, then k1 is equal to minus k2, then q is equal to k1. Right? k2 is equal to minus k1. In the centrum of mass. So K1 is approximately Kf and K2 is approximately Kf. So Q is then also equal to Kf plus delta Q. Q square over M is equal to Kf square over M plus 2 Kf delta Q over M. And I will drop term delta Q square. I will drop it. So in this integral, I have 1 is equal to modulus V. I will take the integration. Limit I will put a little bit later. So the integration is in a spherical coordinate system. I will write, so this is 8 pi cube. In the spherical coordinate system, I will write 4 pi k square dk square. K is already on the Fermi surface. So this is 4 pi kf square. And this is delta Q. So what I have here is Q square over 2m. This is twice Fermi energy. So 2 Fermi energy plus 2 kf delta Q over m minus energy. So this is the object which I would like to have. I will introduce E capital, which is 2EF minus E. And if I find that this curly E is positive, it will mean that the energy is smaller than the twice Fermi energy. So I have a bound state. So this is then integral modulus V 4 pi 2 pi 2 pi square kf square integral d delta q 2 kf delta q over m plus Curly energy. So now with the limits of interaction. The limits of interaction is given by epsilon q minus epsilon q1 is smaller than h omega d. I assume that q1 is on Fermi energy. So epsilon q then is kf over 2m plus kf delta q over m minus Fermi energy. This means kf delta q over m is smaller than h omega d, which means that delta q modulus is smaller than m, let me drop h bar, over kf. So therefore in these limits, this is from minus m omega d over kf to plus m omega d over kf. This is how delta q changes. Again, from minus m omega d over kf to plus m omega d over kf. So I will introduce a new variable x, which is x is equal to 2 kf delta q over m. Therefore, I need to multiply and divide let me repeat it here. 1 is equal to v divided, multiplied by kf square over 2 pi square. I will multiply by 2kf over m and divide m over 2kf. So then the integral is dx x plus e. So since I multiply and divide, so then this is 2 omega d minus 2 omega d. that's it. So first of all, I cancel this. Second, with your permission, I will write 2 and change this limit to 0. Because I can break it to two integrals. Yeah. So this integral, as you see, is logarithm. By computing this integral, I assume that the Curly epsilon is much smaller than the upper limit. We will see that this is correct. It is exponentially small. So what I get then is 1 is equal to V times mkf divided by pi square. This is the density of states of the Fermi energy. So I have 1/2, and I have a logarithm over 2 omega d plus E divided by E. So for the moment, it's still exact result on the right-hand side. But as I said, let me for the moment drop this term. And what I find is that epsilon Curly is twice omega d by e to the power minus 2 divided by modulus V, density of states at the Fermi energy. So what I found is that this epsilon is bigger than 0, and indeed from this solution I see that this is exponential factor, so epsilon is indeed much smaller than the Debye frequency, and therefore it's legitimate to drop it here. So I made an assumption, did a calculation, and now I'm making a step back to check whether my assumption was correct or not. So, to conclude, I found that this is positive, which means that the energy eigenvalue of my Schrödinger equation is smaller than twice of Fermi energy. So the interaction between two electrons in the vicinity of Fermi surface mediated by phonons reduced the energy. There is a bound state. So this bound state is a Cooper pair. Okay. Now let me add a few words. I did some calculations today. I came to some conclusion. And on Friday I will show you that although the spirit is correct, the general conclusion is wrong. So in the vicinity of the Fermi surface, indeed there is attraction. But what happens then, I will need to find the size of Cooper pair and compare it with the interatomic size. I will do this on Friday, and you will see that the size of Cooper pair, which is correlation length, is much larger than the typical distance between electrons, which means that the Cooper pairs are strongly overlapped. So it's too naive to speak about true bound state of electrons. In fact, what happens is that the ground state of fermions in the presence of attraction is unstable with respect to the phase transition. You will see that there will be spontaneous symmetry breaking. So in fact, there is no bound state. But there is spontaneous symmetry breaking phase transition where the ground state is no more the Fermi liquid, but the ground state is superconductor. We will discuss it on Friday. However, the gap and critical temperature, which we will find, satisfy precisely the same equation. So you will see that Tc is then proportional to Debye frequency. You will see it. And therefore, it also explains the isotopy. Together with Tc, there is a gap which is also proportional to Debye frequency, which explains the specific heat and tunnel junction measurements. So, this is what we plan to do during this week and partially next week. But the strategy will be like that. On Wednesday, I will present you macroscopic phenomenological theory, which is called Ginzburg-Landau theory and derived to Ginzburg-Landau equation. There will be no any microscopic theory, but I will rely upon the fact that there is Bode parameter with a wave function of a Cooper pair, and I will express the free energy in terms of the wave function of Cooper pair. We'll minimize it with respect to vector potential and Yeah, and derive equations, Ginzburg-Landau equations. On Friday, we start with the Hamiltonian, which I derived, namely that this is called BCS Hamiltonian because of Bardeen, Cooper, and Schrieffer, three gentlemen who got a Nobel Prize in 1971 for the theory of superconductivity. And then, based on this Hamiltonian, we diagonalize it, do in field, and find a gap and find a spectrum. This will be part of microscopic theory. Any questions regarding to what we did today? You should work hard. I mean, look, of course I have some notes, but basically I do all my calculations in front of you with there. If you have kind of real misunderstanding of what we are doing, please ask questions. Because when you understand what to do, and you know how to do, you do it. And then you get a result. And then we discuss physics. But if you don't understand where we go, or you have a technical problem with doing calculations, ask me. I need to see feedback. Think about it. Repeat these calculations. Moreover, try to repeat these calculations assuming that there is a finite angle. So now I will say that the second electron is here. So this is K1, K2. So then this would be Q. And this, I need to write on the line. This then would be K. So this, this would be 2Q, and this would be K. So try to repeat these calculations assuming that K is finite, not equal to 0, and try to find the solution when this bound state disappears. It will actually be the critical velocity of your Cooper pair where the bound state is destroyed. Good. That's all for today. See you on Wednesday.